renewable energy research, something you actually brought to us. It's all about squeezing more power out of sunlight, looking at the parts that typical solar panels, well, they just miss. This whole deep dive comes straight from the sources you sent over, focusing on light frequency upconversion for enhanced solar power. So our mission today, unpack what light frequency even means for energy, look at these really interesting ways to increase light frequency that's upconversion, and then, get real about the potential and the problems for solar.
Exactly. And it really boils down to the physics of light itself. Quantum physics, actually. Understanding how a photon's energy is tied to its properties. Well, that's fundamental if we want to get more efficient.
Okay, right. Let's start there then. Light obviously carries energy. We see it everywhere. Plants use it, solar panels use it, it heats things up. But it's not like all light is created equal, energy-wise. What actually determines how much energy a single packet of light, a photon, has?
You got it. It's all about the frequency. The core idea is Planck's equation, E equals hf. E's is energy, h is just a number, Planck's constant doesn't change, and f is the frequency.
Frequency, like how fast the wave is oscillating.
Precisely. So higher frequency, f goes up. The energy E of that photon goes straight up with it. Simple proportion. And since frequency and wavelength are, inversely related, higher frequency means shorter wavelength. You can also write it as E equals hc over lambda. Lambda is wavelength, c is the speed of light.
Right.
But it's the same core concept. Higher frequency or shorter wavelength means more energy per photon.
Higher frequency, shorter wavelength, more energy.
Okay. And the sources had some good intuitive examples for this. Like, we know blue light packs more punch than red light. Makes sense. And UV light, even higher frequency, more energy, again, enough to cause sunburns, break down materials.
Right.
While infrared, down at the low frequency end, has less energy per photon. So understanding this EHF, it really sets the stage for why solar cells struggle with certain parts of sunlight. That's exactly it. Different materials are tuned, you could say, to absorb photons in specific energy windows, which leads us to this fascinating idea. Maybe we don't just have to take the sunlight spectrum as it comes. Maybe we can tweak it.
Tweak it? You mean actually change the light itself, take the lower energy stuff and boost it. What does upconvert actually mean here?
Yeah, that's pretty much the gist of it. Photon upconversion. It's a process where you take, say, 2 or sometimes more photons that have low energy.
The ones the solar cell might miss.
Exactly, the ones that might be too weak on their own. And through some physical mechanism, you combine their energy to spit out one single new photon that has higher energy. You're basically giving the light an energy boost.
Okay, boosting light energy. Sounds complex. How do you actually do that? The sources mention a few different ways.
Yeah, there are distinct categories. One major way is through what are called nonlinear optical processes. These usually need really intense light interacting with specific kinds of materials. Think lasers.
Lasers, okay. Not exactly sunlight levels.
Generally not, no. The material's response to the light isn't linear, it's more complex, allowing photons to sort of interact. Second harmonic generation, or SHG is a key example. You shine intense light of one frequency, F, into the material, and it can actually double it, emitting light at 2F. The source mentions turning infrared laser light into green light, for instance. Requires careful setup, phase matching, high power.
I see.
Then there's some frequency generation, SFG. Similar idea, but you mix 2 different input frequencies, F1 and F2, and you get an output frequency that's the sum, F1 plus F2. Like mixing IR and visible to maybe get UV is one example mentioned.
Which still needs that high intensity, though.
Generally, yes. Very powerful for specific applications, but maybe less practical for just ambient sunlight. Which brings us to the second main category, which could be more relevant for solar. This involves upconverting materials. These are usually solids like special crystals or glasses, and they have specific atoms embedded in them, often rare earth ions, things like erbium, thulium.
Okay, and how do they work without lasers?
Well, these ions are clever. They can absorb one low-energy photon, jump to an excited energy level, and then, crucially, while they're still there, they can absorb another low-energy photon, jumping even higher. Or energy can be passed between nearby ions.
Ah, like stepping stones for energy?
Kind of, yeah. Or like collecting energy packets. After absorbing the energy from multiple low-energy photons, the ion eventually relaxes and releases that pooled energy as a single photon. But now it has higher energy because it combined the input energies.
Right, and the sources mentioned different ways this happens within the material.
They did. Things like ETU, energy transfer upconversion, where energy jumps between ions. ESA, excited state absorption, where one ion does the sequential absorbing. And even cooperative upconversion, where several excited ions nearby pool their energy together to boost one ion way up.
Okay, so the big takeaway here is these material-based methods. They don't need the crazy high intensity. That seems really important for solar.
That's the key difference, yes. They can operate under much lower light levels, much closer to, sunlight intensities. That makes them a prime candidate for research in this area.
Makes sense.
The sources also mention relativistic effects, like Doppler shift changing light frequency.
Right, if things move near light speed.
Yeah, but they correctly state that's just not practical at all for making power on Earth. Interesting physics, but not a solar solution.
Got it. So nonlinear optics needing lasers and these special materials using sequential absorption or energy transfer. Those are the main ways. But before we connect it fully to solar panels, what are the general roadblocks? Making any of these upconversion things work efficiently, it seems like it would be hard.
Oh, absolutely. A major challenge across the board is low quantum efficiency.
Yeah.
Meaning you might put in, say, 100 low-energy photons, but you only get maybe one or even fewer high-energy photons out. A lot of the energy gets lost in the process, maybe as heat, maybe the intermediate steps don't work perfectly, maybe the final emission just doesn't happen efficiently.
Okay, so not a one-to-one boost.
Definitely not. Then, as we said, for the nonlinear methods, meeting that high intensity is a big constraint. And for all methods, just finding the right materials is huge. You need something that absorbs the right low-energy light strongly, manages all the intermediate energy steps efficiently, and then emits the right high-energy light effectively. That's a really tough material science problem.
Okay, challenge is noted. Let's bring it back to solar. Why this big push for upconversion in solar power? What's the specific problem it's trying to fix in a standard solar cell?
Right. So the sun bombards us with this whole spectrum of light, right?
Yeah.
UV, visible, infrared, a huge range. But a typical solar cell, like silicon, which is most common, has what's called a band gap. Think of it as an energy threshold. For silicon, it's about 1.12 electron volts. Photons need at least that much energy to be useful.
Okay, so what happens to the light that doesn't have that energy or has too much?
Good question. That's where the waste comes in, as the sources detail.
Yeah.
First, you have the sub-bandgap photons. These are mostly the infrared photons. They just don't have enough energy individually to knock an electron across that 1.2 HeV EV gap in silicon.
Too weak.
Too weak. So they basically either pass right through the silicon untouched, or maybe they get absorbed but just turned into a tiny bit of heat.
Sure.
Useless for electricity. For silicon, that's light with wavelengths longer than about 1,100 nanometers.
A significant chunk of sunlight, right?
A very significant chunk, yes. Then there's the opposite problem, thermalization. This happens with the high-energy photons, blue light, UV light. They have way more energy than the 1.2 HeV EV needed. They easily kick an electron across the gap, but they kick it way up high, energetically speaking. And that electron very quickly loses all that extra energy above the band gap. It just relaxes down to the edge of the gap and the excess energy. Lost as heat again.
Wow, so losses on both ends. Too little energy is wasted. Too much energy is also partly wasted.
Exactly. And upconversion is primarily aimed at that first problem, the sub-bandgap photons, the infrared ones that are too weak. The core idea is, let's collect those weak photons and give them the energy boost they need to get over the band gap hurdle.
Right. So the theory goes, you catch 2 or more of those weak IR photons, use the upconverter material, combine their energy, and out pops 1 photon that is energetic enough for the silicon cell.
That's the concept in a nutshell. You'd have an upconverting layer positioned strategically, maybe behind the cell, maybe integrated. It grabs those IR photons the cell would ignore. It does its upconversion magic using those mechanisms we talked about, and emits a new photon, maybe in the visible or near IR range, but crucially with energy above that 1.12 E band gap.
And the solar cell sees that new photon just like any other useful photon.
Precisely. It absorbs it, generates an electron-hole pair, contributes to the current. So the potential benefit is pretty clear. You're effectively harvesting photons that were previously wasted. More usable photons should mean more current, higher overall efficiency. Theoretically, this could even let solar cells break through traditional efficiency limits, like the Shockley-Queisser limit, which assumes you can't do this kind of spectral manipulation.
That really does sound elegant, getting around a basic limitation. So practically, how would you actually build this? Where does the upconverter layer physically go on a panel?
Yeah, the sources mention a few design ideas people are testing. A common one is putting it behind the solar cell. You'd use a bifacial cell, one that can absorb light from the back too.
Yeah.
So sunlight comes in the front, cell absorbs what it can. The low energy IR that passes through hits the upconverter layer stuck on the back. The upconverter absorbs that IR, generates higher energy photons, and shoots them back into the rear side of the solar cell.
Clever. Using the light that went all the way through.
Exactly. Another way is integration, maybe mixing up converting nanoparticles right into one of the cell layers or applying it as a special coating somewhere.
I see.
And this whole idea fits into a broader concept researchers talk about spectral shaping,
Mm-hmm.
using things like upconverters and also downconverters, which do the opposite, splitting high-energy photons into multiple usable ones to basically tailor the sunlight spectrum.
To perfectly match what the solar cell wants.
Exactly, to maximize how much of the sun's energy the cell can actually convert, minimizing those sub-bandgap and thermalization losses.
It really paints a picture of a much smarter solar cell, one that actively manages the light it receives. But, okay, here's the big question. If the theory is so neat, why aren't these upconverting panels on every roof? What are the real-world roadblocks making this still mostly research?
Ah, yes, the reality check. And the sources are quite clear on this. The practical challenges are significant. Probably the biggest hurdle is getting good upconversion efficiency under actual solar conditions. We talked about low quantum efficiency.
Right, needing lots of input photons for one output.
Yeah, and sunlight, while powerful overall, is quite diffuse. The intensity isn't that high compared to lab lasers. So even for the material-based methods that don't need lasers, their efficiency often drops way down under normal sunlight levels. It might work great in the lab with concentrated light, but put it on a roof.
And you don't get enough boosted photons out to make a difference.
Or enough to justify the costs. Yeah, that's a major issue. Then there's broadband absorption. The wasted infrared light covers a pretty wide range of wavelengths. But many current upconverter materials only absorb strongly in very specific, narrow bands.
So they only catch a small fraction of the potentially usable IR light.
Exactly. You want something that can gobble up a much wider slice of that wasted spectrum. And then the light they emit the upconverted photon, its wavelength, needs to be perfectly matched to the solar cell. Ideally, just above the cell's bandgap energy. Too high, and you just reintroduce thermalization losses in the cell itself. Getting that precise tuning is hard.
Okay, efficiency, absorption range, emission matching, what else?
Well, durability and stability. These things have to last 25, 30 years outdoors. Sun, heat, cold, rain. Many of the advanced materials being explored for upconversion just aren't proven to be robust enough for that kind of lifetime yet. They might degrade.
Right, that's critical for solar.
And always cost. Adding an upconverter layer, using potentially expensive rare earth materials, integrating it into manufacturing. It all adds cost. The efficiency gain you achieve has to be big enough and the cost low enough to make economic sense. Right now, that balance isn't quite there. The sources also mentioned that for some promising materials, you might still need some light concentration lenses or mirrors to boost the intensity enough for decent efficiency, which adds complexity, tracking systems maybe, cost again.
Yeah, takes away from the simplicity.
It does. And just the integration itself can be tricky. You put this extra layer on, you have to make sure it doesn't accidentally block or reflect useful light before it even reaches the main cell. Avoiding those parasitic losses is important.
So it could potentially hurt performance if not done right.
It could, yeah. And finally, there are losses within the upconverter itself. The energy might get reabsorbed before it escapes, or just lost as heat through non-radiative pathways.
Wow, okay. That's a lot of hurdles.
It is. So research is pushing hard on all these fronts, developing new materials, nanoparticles, quantum dots, maybe offer new possibilities, finding ways to integrate them better with silicon, or maybe newer cells like perovskites. But the sources really emphasize that this is still very much in the R&D stage. People have shown it works in labs, they've measured small efficiency gains on cells, but getting a significant cost-effective boost under real-world conditions that justifies mass production, that's the challenge they're still working hard to overcome. It's not commercially viable yet.
Okay, so it's a journey. We've gone from the very basic physics E=hf all the way through these complex nonlinear and material-based methods for boosting photon energy, and seen both the really compelling potential for making solar cells better by using that wasted infrared light, and also the pretty daunting list of practical challenges that still need solving.
That sums it up well. The physics is sound, the goal is worthwhile. But the engineering and material science required to make it practical and cheap. That's where the hard work is happening now.
So thinking about this spectral shaping idea, tailoring the sun's light perfectly for the cell, and makes you wonder, doesn't it? If we eventually crack this, if we can efficiently upconvert the low energy light, maybe down-convert the high-energy light and feed the solar cell exactly the photons it wants. Does that change how we even think about designing the perfect solar cell itself? Or does the main engineering challenge just shift to creating that perfect, cheap, durable spectral shaping layer on top? What part of this whole picture, the potential or the challenges, really sticks out to you after diving into these sources?